Today, I'd like to introduce PoseAdapt, a project focused on making human pose estimation more sustainable by using continual learning techniques. In this work, we aim to develop benchmarks and tools that help models adapt over time without forgetting previously learned information. The key idea is to enable systems to learn continuously from new data, improving their accuracy and robustness in real-world applications. You can find more details, including the resources and code, on our GitHub page. Models trained on static datasets like Coco are built with the assumption that the environment they operate in remains constant. However, in reality, conditions like crowd density, lighting changes, or different sensor inputs fluctuate a lot. These shifts cause immediate drops in model performance, as shown in the graphs where accuracy decreases significantly under changed conditions compared to the reference data. This brittleness means that even if a model has state-of-the-art accuracy in the lab, it quickly becomes unreliable in real-world scenarios when faced with minor changes in the data distribution. So, focusing solely on accuracy without addressing adaptability limits the usefulness of these models outside controlled settings. Common pose datasets vary widely because they have different skeleton hierarchies, labeled body parts, scene crowdedness, lighting conditions, and other factors. These differences come from the need to address various downstream tasks. Traditionally, we train one separate model per dataset, which means we end up with duplicate models and no single model that captures everything. This also means the benefits from training on one dataset don't carry over to actual use. More recent approaches try to combine datasets into a single cocktail and train one model on all of them at once. While this joint training shares knowledge during training, it requires retraining from scratch whenever new data arrives, and it assumes you still have access to all the old data. On top of that, the computational cost grows very quickly as more data is added. So, both methods waste resources in different ways and don't scale well to the real-world variety and continuous updates in human pose estimation. Continual learning helps us keep what a model has already learned while allowing it to adapt to new types of pose data, like body or face-specific information, without starting over completely or just fine-tuning in a way that might cause it to forget previous knowledge. This approach uses less computational power than training a new model from scratch and avoids issues like catastrophic forgetting, where the model loses earlier skills. The PoseAdapt framework is designed as an open-source solution that makes it easier to adapt human pose estimators continuously and sustainably. It's built on top of MMPose, which allows it to plug into any pose estimation model and apply continual learning effectively. The core idea is to handle adaptation on two fronts: domain shifts like different lighting or sensor changes, and structural or class shifts such as skeletons growing in complexity. The framework works in a cycle starting with initialization, where a teacher model is frozen and copied from the last experience. Then, during adaptation, a student model, which is a trainable copy of the teacher, adjusts within a limited computational budget. To prevent the model from forgetting what it has previously learned, it applies a regularization step where a penalty is calculated to keep the adapted student model close to the teacher. Finally, the framework updates its statistics to finalize the current experience before repeating the cycle for the next one. This process ensures the model keeps evolving without losing its past knowledge. There are three key regularization strategies we use to help the model retain knowledge while learning new tasks. The first one, elastic weight consolidation, identifies which parts of the model are important for previous tasks and essentially locks those weights, allowing only less important connections to change during training. The second method is learning without forgetting, which uses knowledge distillation. Here, the new model is guided by the old model, sometimes called the teacher. Finally, less forgetful learning focuses on the internal structure of the model's feature maps, encouraging the new model to maintain a consistent way of interpreting features by constraining the geometry of these maps, which helps it see the world in a stable, continuous manner despite adapting to new data. To encourage researchers to develop pose-focused CL methods, we propose a domain adaptation challenge. Using a fixed model, data size, and training budget, we systematically test the effect of CL strategies when adapting from a reference domain to these challenging domains. The adaptation scenarios include changes in scene density, where more people and synthetic occlusions appear, lighting conditions with progressively lower light levels, and modality shifts that simulate sensor changes like grayscale or depth cameras. Here, we see the results from the PoseAdapt challenge focused on domain adaptation across three different benchmarks: scene density, lighting conditions, and modality variations. The table compares several methods: fine-tuning, EWC, LFL, and LWF, based on accuracy and adaptation performance metrics. For scene density, the challenge tests models on light to heavy crowding and occlusion, where we notice that LWF tends to maintain higher accuracy, especially as the scenes grow more complex. In lighting, which ranges from low to extremely low brightness, the same adaptability trend appears, with LWF generally performing better at handling progressively darker conditions. For modality shifts, including RGB, grayscale, and depth images, LFL and LWF show improved accuracy over basic fine-tuning and EWC, highlighting their strength in adapting to different sensor inputs. The table also differentiates between reference domains and target domains requiring adaptation, emphasizing the challenge of sustaining performance while facing these changes. Overall, this data highlights how regularization-based continual learning strategies can better manage domain shifts compared to naive fine-tuning, which can struggle under strict resource constraints, especially when adapting sequentially. This reinforces the importance of choosing effective adaptation techniques to build robust, sustainable pose estimation models. The transition from RGB to depth data is the toughest challenge in our benchmark because depth images lack the texture present in RGB, making it much harder for models to adapt. The pre-trained model performs well on RGB with a 70 AP, but when adapting to depth, all standard methods struggle significantly. Despite this, continual learning-based adaptation still does better than simple fine-tuning, showing it has potential as an alternative approach. The results also highlight that while regularization helps with changes in appearance like lighting or occlusion, it fails to manage the complete geometry shift seen with depth data. This indicates a significant modality gap that current methods can't bridge, pointing to the need for new continual learning strategies specifically designed to operate effectively within our computational limits. In addition to the domain adaptation tasks we've discussed, we propose a class incremental challenge called Body Parts, which focuses on skeleton growth by integrating new key points over time. However, it's important to note that we do not include benchmarking results for this class incremental challenge in the current work, which is left for future work. Models that remain fixed over time no longer meet the needs of real-world applications, which require ongoing adaptation and evolution. It's encouraging that this adaptation can be done sustainably, with minimal need for additional data and computational resources. Among various methods, learning without forgetting, or LFL, stands out as the most effective approach, providing stability through feature-based regularization. This makes it a strong candidate for future adaptive systems that need to balance continual learning with efficient resource use.